Select neural principal component analysis prepared by Anastasia Tkachyshyn and Nadiya Shvai. The presenter is Anastasia Tkachyshyn. Anastasia, you're welcome.
Thank you. Hello, dear colleagues, and Vitaliy already presented my work, and again, I would like to present it, and it was written by me and my supervisor, Nadiya Shvai, and please, could you go to the next slide? Okay, so let me begin by establishing the foundation of our work. It is image classification problem. It is the problem that drives our research, and image classification is pretty one of the most important and fundamental task in the computer vision. Given one image, we need to assign it somewhere to the predefined class or category, and this task is really applicable in a lot of areas. And for example, I can provide you example for, that in medical services it's really important because it helps to analyze tissue and probably find some tumors, whether they are healthy or not. Additionally, it is really important in automatically driven cars because the system should identify the signs, pedestrians, cars on the go, and it should be pretty precisely. And yeah, and our research aims to make the classification faster and possibly easier. Could you please turn to the next slide? Thank you. And we know that for the image recognition and for the computer vision in general, we need to have the data. And the more data, the better is our training. However, we face the problem where we meet some constraints in terms of time, in terms of energy consumption and memory. And that is why our research appeared. And additionally, I would like to add that on the other hand, when we try to reduce our dataset, we face with the problem of the worsened quality of our training, and we would like to find some compromise between the efficiency and the quality. Yep. And our probable answer to this problem is Coreset selection. It is a method of selecting smaller subset within the larger dataset, and its main idea lies in its name. It basically selects some points in the dataset called cores and selects any other points that make these smaller corsets, and as the result, they form a full smaller subset. Yeah, good. Next. Thank you. And here comes our problem formulation. We address our problem as the Coreset selection one and data distillation one because we compose a smaller data set out of the larger data set, and hopefully that we include all the knowledge from the larger one and make it pretty qualified. And we propose Coreset selection method that is based on class-wise neural principal component analysis. We are inspired by the work of Yannick Neuhaus, who presented this method, and our Coreset selection is mostly based on it. And it works the following way, that we select our principal components, and the next we select images that are data that are the most suitable for the components, and in this way we select our smaller subset. And our goal in this work is to find out whether we manage to create such a good subset that it will provide our qualified results. Next. And I would shortly note the key work contributions. First of all, we show our new NPC-based Coreset selection method. Secondly, we evaluate our approach on two datasets, ImageNet and C410 datasets. And lastly, we compare our performance against Herding, A, K, and K-centered greedy. Next slide, please. And here comes our methodology. As I told, it is based on NPCA, and its principle lies in the way that we select some principal components and data that that represents those components the best way, and after that we select, we hope that we select the best representative data points in our subset in our dataset, forming the subset. Next, please. Yeah, and first of all, it lies in the way that firstly we extract raw feature from the penultimate layer of our neural network, because we still need the system to know the features, not the defined objects. After that, we make a class-specific weighting, showing how much our image correlates with the class. After that, we calculate class logic that shows us how much the image contributes to the class itself. And after that, we compute class prototype, which is basically the mean of all the class-specific weightings. And it shows the general pattern of the class. Next, please. Thank you. And after that, we compute feature deviations. It basically shows how much our image differs from the general cross pattern. And this deviation we form into our covariance matrix that shows how the features covariate within a single class. And after that, could you please, next slide? Thank you. And after that, I will not explain you all these calculations. However, general idea lies in the way that we transform this covariety into elements of the matrix into the computations, how the components play significant role to the class. Yeah, shortly it looks like that. Next slide. Thank you. And after that, we calculate our main variable. It's alpha, and it consists of two parts. First part is the sum of all eigenvectors, and it shows how much the component contributes to the class. And the second one shows how much of the components consists in the image, how much of the image contributes to the components, I would say. And lastly, we perform our Coreset selection. Having created our images by the alpha, we select the best ones, and our subset size depends on the size we choose. Next slide, please. Thank you. And now I will talk about datasets. We have used the ImageNet and C410. ImageNet is a huge database, and I have selected one that was for image classification challenge made in 2012, and it consists of 1,000 classes, approximately having 1,300 images, and it was honestly a little bit too much for my computer, and I have used those first 10 classes. The image resolution is 224 by 224, and it was resized for the easier operations. And additionally, I have used C410. It's a standard dataset. It has also 10 classes, 5,000 images each, and its images are pretty simple. They are 32 by 32 pixels. Next slide, thank you. And I will show you some Coreset selection results. At first, it will be the classes, the example of the class we have selected. And secondly, I will show you some CRAD-CAM heat maps showing which components were highlighted as looking for. Next slide, please. Thank you. Here is the example of subset from ImageNet. We have selected one image per each class, and we see here tench, goldfish, white shark, tiger shark, hammerhead, electric ray, stingray, rooster, hen and ostrich, and it basically what the system sees as the best images that present the class. And we can see that some of them are pretty obvious, like we see definitely here goldfish or hen or ostrich. However, something is wrong with tench. We see holding a fish here, and probably the white shark is not really recognizable as it could be. And I think I will talk about it a little bit later. Next slide, please. Thank you. And these are the subset from CIFAR 10. We can see here plane, car, bird, this is cat, deer, dog, frog, horse, ship, and truck. Those are 32 by 32 images, that is why they're not so clear, but these are the ones that our program seems to represent the class the best. Next slide. And now I will show you some Graham visualizations, the heat maps that shows us the components selected from the class. And I will show you some successful cases and not so. Next slide, thank you. And first of all, we see here goldfish class. And I consider it as a pretty successful selection, since we see here, for example, on the largest image, the first image shows it is generated image that shows features that are basically like our components, and heat map shows what it highlights the most. And we see that the most highlights are in the area of fish face, on the eyes, and on fish tails somewhere. And on the second component, we see that mostly the system searched for some fins, for some tails, and for fishes in the group. And we see some patterns here because there's a lot of fishes photographed about from the water, or just fishes, as we can see here that the most highlight goes to its tail and fins. Next, please. And lately, we see that we highlighted mostly the fish scale, and again, fishes in the waters and mostly in the groups. And on the first component, again, fish scale, and even we can see on the generated image that it forms a figure that is similar to fish body, and it has something similar to its scales, and that is what the heat map pays the most attention to. Next. Thank you. And basically with each component, the prediction and the component that basically the system search for is less significant. And now we can see that it is some fins, tails, and upper face of fish. So that is mostly captured. And next is just fish eyes. Next. Thank you. And here are last components, and we can see how we lose the pattern with each component. And the last one is, I think that is pretty meaningless because it has some pattern, it has some bunch of fish, and it has it captures fish face as well. However, we also see fish in glasses. And I think that the generated picture also has included those glasses like blinks and forms. So probably this is why it captures it. Next. And now is an example of pretty unsuccessful, I think, subset selection. However, luckily, it didn't happen with almost every class. Most of the classes were successful, and it mostly was for white shark and tiger shark. And I think that might lie in the fact that the image quality and most of the images were not so good, because, for example, we can see that on the first component, the system mostly captures splashes and not real fish, and we can see that where there's a fish on the images, it mostly highlights its splashes, and on the second, it mostly captures cage, and that's it. And it's pretty funny because here it captures fish stripes and is misinterprets it with cage. Next, please. Thank you. And on the third component, we see some decent results, I think. And we see finally a fish body, we see a fish face, and on the first component is also pretty well, I think. We see it mostly captures some festies, and yeah, however, I think that it still misinterpreted it with fish splashes, since the third image of the selection and first one, I mostly splashes. Yes, next please. Thank you. Here again, something here again, and it shows how the system misinterpreted shark with cage. On the sixth component is pretty again successful. It's captured fish face. Next, please. Thank you. And here, what I find interesting as well is on the second picture, the system captured fish shadows, water shadows on the flashback, and I think that it thought that it is still a cage, however, it isn't. And on the eighth component, we started losing the pattern because we see here a bunch of different images from different categories, and we cannot really describe what was the component. Next slide, please. Thank you. And the last one, again, I think the last two were more successful than the previous ones. However, they are still pretty insignificant. And next, please. And now we have great hand visualization for Shpir 10. I think that I will not talk a lot about it. However, it's still, at first, it pretty well captures the cars by first two components. Next slide, please. Thank you. And yeah, it still continues to capture it pretty well. Next slide, please. Yeah, and after that, it starts losing its own pattern because on the first component, it doesn't really see the component. However, it still has shown the images. And on the sixth component, it's just the heat map highlights anything but a car. Usually, it's some sort of background or the cars with white in it or some sky. Next slide. Thank you. And next, we see that, again, some of the component performs pretty well because we still see a car. The eighth component, we again start losing the pattern and we don't really see anything highlighted. Next slide. Yeah, and surprisingly, on the 10th component, it starts working pretty well again. Next slide. The next slide is with dogs. It works pretty well. However, I would like to show you one thing that is pretty interesting for me is here nothing special occurs. However, the system works pretty successfully. It highlights the dogs. And next one, please. It's these two components because they are one after another, and the system didn't highlight anything. However, it just included some of them mirrored versions of same images, or they were to be scaled. I think that is because the system still sees some patterns in here, and that is why it has chosen such similar images and in neighboring components. Next slide. Thank you. And yeah, after that, it again performs pretty successfully, I think. Next slide. Yeah, and on the almost last component, it again starts to losing its pattern, and we even don't see any similarities with within the components. Next slide. Yeah, and here we have almost lost the pattern. However, I still see that in 9 components it mostly selects white dogs. However, it captures again the backgrounds mostly, and the 10th pattern, the 10th component is not really significant. Next slide, please. And now I would like to talk about comparative method that we decided to compare our method with. Next slide. It is heading. It is algorithm that it basically selects samples one by one, and it is chosen in this way that it minimizes the distance between the current subset's mean and original dataset's mean. Next slide. And K-centers greedy, that's an algorithm that starts with selecting some random data, and after that it chooses iteratively samples that is farthest from the previously selected samples. Next slide. And here we have our experiment set up. Additionally, I would like to add that we created subsets with 1, 5, 10, 20, 50, and 100 images per class for each of the dataset. And we used for our training ResNet 50 for ImageNet and ResNet 34 for CFAR 10. And after that, all the parameters are pretty the same. We used 50 epochs, batch size 64, and optimizer Adam in order because they were pretty popular choices, and we considered them as the most optimal ones. Next slide. Thank you. And here we have our comparative results. We see that our NPCA-based method worked the best for the significantly small subsets when we have chosen 1, 5, 10, and 20 images. And after that, it was outperformed by Kate centers. Yeah, next slide, please. Thank you. And here we see that for CFAR10, our method was not the best one. At first, Kate centers was performed pretty well, but after that, Herring outperformed it. However, I want to note that on the images 20, 50, and 100 per class, we had pretty we have some difference, but it was up to 4%. Next slide. And that is why I would like to make a conclusion that I think that our method can be good when it comes to selecting really small subsets and when it comes to working with difficult examples with more difficult problems. Yeah, so in case just if you want to create a really small subset and with ImageNet and you want it to be pretty effective, you can select this method. And that's it. Yeah, thank you for your attention.
So, Anastasia, in the beginning of your talk, you said that you choose algorithm using some trade-off between speed of processing and effectiveness. What's algorithm from your point of view will be most appropriate to this criteria?
Honestly, based on the training data and on the comparison, I think that Kacen Gritty is one of the best because it captures pretty diverse images and it shows as much as possible out of the whole dataset because it selects the furthest point and in this way it captures as much as possible.
Do you measure this quality of each algorithm? You demonstrated some table, but without abbreviation of indexes for each algorithm.
It was, I performed ResNet and it was based on training data that was our subset and validation data from the original datasets. And I performed the accuracy, the training prediction accuracy. Yep.
Some other questions? You're welcome.
Thank you for a very interesting presentation. The question is the following. It is evident that the results of presenting the class in the explicit form strictly depends on the distances between corsets. Did you analyze this aspect?
I think that's probably not really. Yeah, that's it.
This is planned for the future work, for instance.
Exactly. Yeah. Yep.
Yes, I do have one.
Please.
Thank you for a nice presentation, Anastasia. My question is about the recent trends. For example, what do you think about comparing your approach with the latest diffusion models that are used in the community for image classification?
We always strive for better and for something that work for us.
I just need a nice table from a leaderboard on image classification. For example, on ImageNet, showing the current state of the art. What are the accuracy figures? Do you remember? In the current state of the art, not depending on the class of a model. Okay. What is the current state of the art in the accuracy of image classification? Mhm. It's a microphone just in front of you. You may use it. In front of you. The microphone. Sorry for interrupting.
Works? Oh, okay.
Fine.
And yeah, in this work, the largest the training accuracy on a whole dataset was 60 somewhat percent, I think.
Do you have maybe some benchmark to compare the results and something?
My benchmark was. Could you please share the presentation? It was the yeah uh, back. Oh. Mhm. My benchmark was my own training results. It was here. We see for cipher 10 91%, and can you go back? Yeah, 77%. And however, it was not for whole ImageNet. It was just for first 10 classes. That is why it is. I think probably so good. I don't know because I think that on the larger datasets, the accuracy quality might be worse.
Thank you. So it's a training set or test set?
Training set.
Training set. Okay. Thank you. So if the questions are absent, many thanks. It's very interesting presentation. And we will go to our next presenter. The paper is named by text-to-image license plate generation with latent diffusion models prepared by Mariia Shpir, Nadiya Shvai, and Amir Nakib. So the floor is yours. You can.
Thank you, everyone. Okay, I'm going to be checking from time to time my phone. This is just to time myself to try to finish on time. Okay, so me, I'm Nadiya Shvai. I'm going to be talking today about license plate generation. So just to give some context, I work in the field of the computer vision. More specifically, I work with deep learning methods. And I work in industry. So I work in France for Cyclope.ai, which is a subsidiary of Vinci Autoroute. Additionally to this, I mentor students mostly from National University of Kyiv Mohyla Academy. And this is a joint work actually in the scope of the Sigma project, which I'm going to talk more about in the end. So this is the presentation of the result of 9 months of work jointly with mostly with me and Mariia. And Mariia is, at that time, she was a bachelor level student. And finally, in cooperation with Amir Nakib, who is a professor in UPEC in Lycée Lab. Okay, next slide, please. Okay, so we're going to be talking today about very, very practical topic. and it's going to be license plate recognition, meaning that if I have a video or image of a license plate, I want to be able to produce a number of this license plate. Why do we want to do this? Well, for traffic management, for security reason, law enforcement. For example, when you're using the parking and you're just entering the parking without having to take the ticket and then you leave, right? And then you pay when you leave. So just based on that on your license plate being recognized. So this is a very easy example of how it's used in the industry. However, there's a problem with this. It's access to the data. So Anastasia, who spoke before me, she touched a little bit on the topic of the complexity of accessing big amounts of data. You have to store them, you need to label them, and additionally, there's a privacy concern, right? So particularly in US, in Europe, in Japan, there are quite strict regulation, like how you can collect the data, what kind of data, how long can you store it, and so on and so forth. Can go to the next slide. Okay. This is an overview of the existing dataset on the license plates. So you have the dataset name, number of images, and then the origins and type of annotation associated with it. So if you look at the amount of images, actually these datasets are pretty small if we're talking about the deep learning problems where number of images, usually they're calculated in millions or at least hundreds, thousands. And the only, like the one more or less big here, this is like Chinese dataset, which is over 300,000 images, and then Brazilian and Iran datasets. So as you can see, like not European ones, right? So what is the one of the possible answers to this like data starvation? So there are multiple approaches. There are different frameworks on training models with like little data available. However, what else we can do? We can provide a synthetic data, which is an excellent answer because once you're able to do a synthetic image, you can produce a lot of them. And even if they lack in the quality comparing to the real images, the fact that you can produce almost unlimited amount of them usually outbalances the fact that they're less than perfect. Okay, so how can we generate license plate? Because license plate is a great example. It's a very easy thing to generate. You can actually like ask a child to draw a license plate and it will be able to draw a license plate. It's just some predefined type of the text into a rectangular box, more or less, right? So the first natural approach is a template-based generation, right? So the problem with this is that it lacks natural variation. You can introduce some with predefined transformations, but it's not going to be very realistic. Still, it's available approach. It's very cheap, right? Once you are able to define the transformation, it's very, very cheap. Great. Second one is I'm talking about the one explored already in the literature. It's generative adversarial networks. Works much, much better. However, it's a bit problematic in the training, so it can collapse quite often. And the second problem, usually the diversity is not very big. Not always, so there's either a problem in the diversity or some other issues regarding the diversity of the output, for example, and the type of the signature of the license plate. And the trend of the last couple of years is using diffusion model for generation of the images. And here we're going to explore exactly this. So next slide, please. Okay, this is the dataset description because we have to train on something. So it was 78,000 images of the Ukrainian license plate. And well, of the format of the type 1 that you see on the left. Okay, next slide. And we're going to first start with the unconditional generation. What does it mean? My goal right now is to generate a synthetic license plate, and I don't really care what number it has, but I want it to look realistic. And in order to do this, we're going to apply the denoising diffusion probabilistic model, which in short is trying to reverse adding noise to an image. Okay. So like if you have a process of adding noise to the image, starting with the clear image on the right, going to the left. The model will try to reverse it, going from the noise to picture on the right, which follows a particular distribution, right? Which we don't want to capture explicitly, but we capture with the model. From the noise, it's able to replicate a sample from that distribution. Great. Okay, next slide. Okay. And this is the output of the model throughout different steps of the training. So different epochs from 0 to 100, you see that with time, it starts to be more and more and more realistic. So with the course of the training, model captures better and better actual distribution of the images. Perfect. Next slide. This is some metrics associated with the generation, just to understand how successful we are. And we said that we're mostly interested in type 1, and we can roughly say that we are successful in 82% of cases, which again, it's great. Like you can 82%, it's like pretty low success rate, but it doesn't matter if I can regenerate image again and again and again, right? So like my only goal will be just to filter out the images that I think that are not really good. Next. Perfect. These are examples of the successful license plate generation. So as you can see, they're pretty realistic looking. Next slide, please. And these are the failures and the different types of the failures. So either it's not readable, meaning that the characters are not real or like not readable at all. Second one, it's not following the template, which should be 2 letters, 4 digits, and then 2 letters again. And then finally, generating non-existent region code. So this is, okay, like here, I really, really want them to be realistic, right? So like actually for the text that we will have in hand, the last one is not important, but if I want them to be real, so we count this also as a mistake. Okay, next slide. Perfect. This is more in-depth analysis of the distribution regarding the characters and the symbols. So we're interested how close does the model capture the distribution that's provided with. And we see that also on the level of the characters, it catches the distribution pretty closely. Next slide. And so the same with the prefixes corresponding to different areas in Ukraine. Next slide. Perfection. Okay, so this is a neat trick. Now I have a model that's able to generate synthetic data. The question is it really useful? And if yes, how do I use it? So how do I assess? Is it useful or not? Because remember, we started with the license plate recognition. I want to read my plate. I actually don't care if I can generate one. So the question is, can I use synthetic license plates to somehow enhance another model, which is going to be in charge of reading the license plate? Well, let's talk about reading the license plate. We can read license plate, like build a model that's going to read license plate in many different ways. Here, we're going to go a very straightforward way. We're going to detect characters, right, in the image. So I will use an object detector that's going to detect every character in a row. And then just going to line up, and I'm going to say that this is the license plate signature. And I'm going to say that it's a successful reading if it's actually the text of the license plate, or 0 if it's a failure. Right? So because you can introduce some sort of partial success. No, it's success or failure, binary. Okay, perfect. Next slide. And we're going to assess the impact of introducing synthetic data in the following way. We are going to take a subset of real license plate, and we're going to train a model only on those. And then we're going to take synthetic license plate, and we're going to add more data, and we're going to see the impact of adding more synthetic data. And at the same time, we're also going to be assessing some hyperparameter or of the model, which is going to be the cutoff detection score. So this is like just explanation for the table that you're going to see now. Next slide, please. Yes, okay. So this is the accuracy at different confidence threshold. Like basically, you're only interested in the best number in every row, so which is going to be the bold one. So here it's right now you can see them as preliminary numbers because this is the validation data set. Next, you're going to see the actual test data set. This is used for the assessment of the optimal confidence score. But you see already from this preliminary results that adding synthetic data definitely improves our model, right? So if I add synthetic data to the training of the license plate recognition model, the accuracy of the reading improves. Okay, next slide, please. Okay, and this is the final result using the estimated hyperparameters. So the previous results were on the validation data set, and this is the result on the test data set. Okay, perfect. Next slide, please. The additional output of this work was also the generated data set of synthetic license plate, which has been released on Zenoda website, which is a great platform for releasing data set or additional materials to the research that you do. So I highly recommend. Next slide, please. Okay. So what are the key takeaways to this part of our work? First, what we have understood or confirmed, diffusion models produce high quality license plates. So if you if the question was, can we use diffusion models for this task? Yes, we can. First, this is the second one. Is this data useful? The answer is yes, it's useful. It significantly boosts the accuracy of the license plate recognition model. So it's good that we can do it. And third, so the result of our work is synthetic data set that one can use for research or private purposes. Okay, next slide, please. Now we move on. So this was like the first step when we just want to generate license plate, any license plate. We don't care about license plate. We know that the distribution is sort of correct. It replicates the real data set, but actually I don't always want to replicate my data set distribution because in real data set, not really the case of Ukrainian license plate. But if you take French license plate, some characters are really going to be underrepresented. So if I could somehow influence what kind of license plate I want to generate, specifically, I want to give a text to model and I want to receive license plate with this particular text. Okay, so for this part of the work, we're going to be employing the latent diffusion models. And training is going to be consisting of two steps. We'll need an autoencoder that is going to capture the representation of the image in the feature space. So roughly it's going to transform my image into a vector, which is much smaller than the image, right? And then I'm going to train another model, which is using this sort of the representation, and the text will be able to generate the image of the license plate with this text. Next slide, please. Okay, so stick with me because there are going to be a couple of technical slides. Just going to do a high-level overview that for the visual autoencoders, we trained different types of the model. Plus, we use the pre-trained model, trying to understand which works better. So I'm on the pre-trained one. The stable diffusion seems to work the best. And then I'm on the specifically trained for our task model. So you see here different metrics, but overall you can say the Kullback-Leibler divergent-based model were better. Okay, next slide. Additionally, at this step, which is quite important, we do the estimation of the parameter that's called the guidance scale. It's a special parameter that tells you the importance of the control, because there is like importance of the control of the characters and then how much you want the image to be realistic. So the value of 1.2 seems to be good, which is actually not a super high control. So if you try to control too much, you see that images start to get less realistic. Next slide. Okay, perfect. Now comparing to some baselines. So the top is the proposed method, and on the bottom you see again type of the model, which works with the explicit control of the characters. When you say on the first place I want this character, in the second place I want this character, etc., etc., etc. So you see that in both cases they look overall not bad, like quite realistic, and like this is for the visual comparison. But some characters are not like fully true to their shape. So we particularly used this text signature because Y is not used a lot, so it's a difficult character to capture, and you see that both models are struggling with it. Okay, next slide. Okay, and then there's some numerical metrics that capture the how realistic is the image. So the first two metrics, it's about how realistic it is, and then the second two metrics, it's about the fidelity to the text that we have provided. So the good news, our approach is better in terms of how realistic the image is, if we look at the numerical data. However, it's worse on the fidelity to the text. But again, this is not necessarily a problem as long as we can produce many images, because you can always filter out the ones that finally are not good. Okay, next slide. Outputs of this part of the slides. We saw that the latent diffusion models, they outperform GANs in terms of the images being realistic. We have quite high control over text to image synthesis. So I would say this is adequate if we want to actually use it in the production. And we saw that the choice of the visual autoencoder is important for this task. So it's not negligible. Like if again, I would like to replicate it for another type of the problem, we would I would predict that we would have to spend some time on this before actually training an LDM. Next slide. Perfect. Okay. I would like to say a few words about the program which helped to finance this work. So it used to be before it was called Mentor Program for the Underrepresented Young Researchers from SPS, Signal Processing Society. Now it has been renamed into Signal Processing Mentoring Academy. My guess, because of the new trends with the Trump administration, etc., etc. But essentially, it's exactly the same thing as before. So what does it do? It provides mentor experiencing by pairing a mentor, so either from industry or academia, with the student, and preferably from different countries. There's a process of matching of the mentor and the student. Like there is an event when you can meet a mentor, or vice versa, you can meet a mentee, or you can just sort of if you already know someone, you can bring a mentor or a mentee to this project. It's a 9 months collaborative research project, and it culminates in a joint publication at ICASP event, which is one of the largest signal processing events. Next slide. And just to demonstrate to you that it's really, really easy to apply, you just need a 2-page project proposal outlining briefly the aim, the budget, and that's pretty much it. It's pretty simple. I highly advise to have a look and maybe try yourself as a mentor or as a mentee. Next slide. Yes. Okay, some links. So for the conditional license plate generation, that is to say text to image, this is going to be the ICTRI paper. For the unconditional license plate generation, there was the paper that was presented last year at ICAI. And the data set that we mentioned, about 10,000 license plates, green license plates, you can find it at Zenodo. Thank you for your attention. Now I'm going to be happy to answer to your questions.
I would like to start the questions, and the first question is: do you research an overfitting problem in your data? Because you talk about small variety and high similarity in the data, and it can be some reason of overfitting. So, did you compare, for example, training and test error or accuracy in your data, synthetic data?
In the synthetic data. So when we were looking, well, actually the results that we have obtained with the denoising diffusion models, we saw that actually diversity is already good enough that when you use an adequate amount of the synthetic data, it's almost the same as real. But for example, if you look at the previous research for the generative adversarial networks, you can see that it just try plainly to replace real data with synthetic. So like the results are going to go down. But again, so ideally, from our experience of what we saw, what you want is some real data and then adding synthetic data. And probably what you want is adding much more synthetic data than the real that you have. So then you will feel the impact, the positive impact.
About your table, in some of your table, you demonstrated that accuracy of real data was higher than synthetic data.
Yes.
Did you investigate this case? And maybe you know reason about this.
Yeah, because I mean, with synthetic data, like you're trying to replicate the distribution of the real data, like you test on the real data, right? So this sort of replication, it's not perfect. If you just try, so if I have like 1,000 real samples and I just want to replace them with 1,000 of synthetic samples, what I can expect that the accuracy is going to go down. It's normal because basically you have changed the distribution of the data on which you are training a little bit, right? So you try to mimic as closely as possible, but it's not perfect. And now there is some sort of domain gap between your training and testing data. They are not identical. It's the same if you have a student that's prepares for the exam and he has a set of questions, and then in the exam, you can have questions that are very, very similar. And then you can have questions that are a little bit diverse. If they're a little bit more different, of course, most likely the student is going to show smaller, like worse performance, right? This is exactly the same idea. But then if you take the same student and you give them similar question to what you have in exam, and then a lot of questions that are not exactly the ones in the exam, but pretty similar, his overall performance is going to increase. Sorry, got carried away. Yeah.
Thank you. Thank you so much for your interesting presentation and very, very energetic information about your results. My question is the following. Synthetic data-based approach is now one of the main way to improve capacity of data. Yes, but key question is diversity, capacity, diversity, and maybe resources. The trade-off. What about your opinion? Which key metrics are important in this trade-off based analysis? Because we use such approach for some other task related to demanding to identify explosive ordnance on the other in different conditions. Hence, we understood that we need develop special techniques to assess quality of synthetic based approach. Hence, to summarize of my question is which key metrics we need to apply to provide a good quality of synthetic data and application of synthetic data-based technique. Thank you.
Hello. Okay. That's really good question. So I guess it depends a lot on your application. So here we're in a privileged situation when we can like train a model multiple times. And so we can understand the efficiency of the generation of synthetic data just by looking at the target task. My final task is the license plate recognition. So the better is the license plate recognition, the better for me personally, the quality of the synthetic data set, right? So this is when I have actual target task that I can replicate and replicate and replicate. This is one scenario. Another scenario, if you just want to generate synthetic data, store it for the future, but you actually don't know exactly the target task. Why is it important? Because if, like, for me, I don't actually care how my images look like as long as they help me with the final task, if it's defined. But if it's not defined, I want them particularly to replicate the real distribution as much as possible. In this more general scenario, more complicated scenario, this is going to be the key metric. How close is the distribution of the synthetic data to the distribution of the real data? So in our case, it's a particular case of the license plate where we're able to see, for example, the distribution of the characters. And we saw that they are pretty similar, which tells me that the model captures really well the distribution of the images. Otherwise, so you can try to look at some other diversity metrics, for example, in the embedding space, but the idea is going to be the same. You want to see if you're able to replicate all the main cases of the real data. So either by comparing the distributions or maybe comparing the main cases, so you can see, you can look at this as the subclasses, etc., etc. It's a bit difficult to talk in general, but just in 2 words, it's going to be the difference of the distributions between the real and the synthetic data. Thank you.
Thanks. So we have some time limitations, so thank you so much.
Thank you.
Very interesting job. So, we have one more presentation, which is titled as Automated Test Tasks Generation by Means of Computer Vision and Machine Learning Technologies, prepared by Ivan Shyian and Olena Havrylenko. You're welcome.
So good afternoon again. Good evening, maybe. So I want to present another work. It's maybe less, not so big scaled, and maybe it's only beginning of the research of me in collaboration with or my PhD student by my guidance. And it's dedicated such a popular theme and maybe problematic, as well as it's popular, it's as well problematic, creating tests. Next. It's obviously that traditional methods of creating tests require significant time and resources from educators. And we try to test how can we use AI existing AI tools to create convenient tools for tutors to automate this task. But not only point attention on their engineering sciences, where we have, besides the texts, we have as well formulas and as well a lot of graphical information, graphs, schemas, UML diagrams, flow charts, and so on. Our researchers show that there are different approaches for different part of such materials. From one side, we may ask ChatGPT generate our question from the microprocessor, from programming concrete schema, but it will be like common question. But each tutor want to have its own explanation, presentation, and want to pass it to their students. Next slide. Our goal is to automate test creation, and it's a small task in the big task of creation of the courses, automated courses of laboratory works or practical works in engineering sciences, like we have theory of automatic control, microprocessors, actuators, where we have stands and different equipment, but in each laboratory training, practical work, we have such a part where we need, before allowing student to solve the task, test its level of knowledge. And we just want such a we have such a brief like test before and after laboratory work. This is the maybe more ambiguous goal. But here we just want to explore conceptual thesis model for thesis generation to make work of generative models more precise, extract and process text formulas and graphs in different ways, then develop adaptive tasks for personal learning, and build some web interface for tutors. In this case, we take Flutter Flow and as low code to have quick results, and it allows integrate Gemini 2.0, I think. Next. Related in the different works, there are a lot about such task like generation of questions. And the main methodical methods which put in the base of such a method is knowledge tree models, which organize concepts hierarchically and then combine them to the component of knowledges, component of skills, and so on, like we always do in our previous system and researchers. And there another approach, semantic categorization, which structure educational content into categories as concept, tasks, and methods. At last, it's this conceptual thesis model that generates tests on the basis of structure and materials using thesis, concept, thesis, thesis, concept, thesis structure. And it shows that it's more effective for the automatic using algorithms, not AI, but algorithms which put the question to the one thesis, to the another thesis, and to the concepts, and give more. And this way, we get more reasonable questions, not just what or which, and so on. Next. And our hypothesis that questions can be generated by integrating AI with this conceptual thesis model. Concept and the related theses extracted from the test or images, and better for using AI, it's better to use graphic presentations, and we may extract using computer vision, extract separately text, separately graphics, and separately formulas. So in this case, we use computer vision. And a key advantage is adaptability, and as well AI allow generate several level of questions. It may be it may then use for the different tasks. So input test, output test, maybe final test, and in different forms. I have idea which I cannot from my postgraduate students get some solution of this idea because there are some complexities that then tests do in the form of some puzzles, like in Duolingo. It's very popular and effective approach. Adaptability that for the students, and we may use this session not only for testing, but as well in training mode, when we show the right answer, for instance, or like we say, diagnosis, make diagnosis about what is wrong in the answer of student. Next. So the system architecture consists of several models, but it based, in my vision, it must be integrated on the base of relational database. Here, this is node of the of this system, which includes users, courses, name, and topics. So as well, we may for the system for the tutor, and as well for students. But now it's only uses for the tutor. Next. And three specialized models and web pages for it. It's for text processing, for formula processing, and for graphic processing. Formula processing is implemented using a LaTeX presentation. Next. And text and graphic processing consist of several stages where tutor upload image, AI construct, generate, extract content, separately text, for instance, or separately image, and generate variants of questions. And tutor only put yes or not, it's valid or invalid, because there are a lot of hallucination in these questions. But for text, this first division on the concepts, thesis, concept, thesis, gives more reasonable question, as it will be shown in during our experiments. And questions then saved in the database and may be reused then. Next. And here you can see like looks the page with their generating questions using the text. So here concept thesis concept extraction, and then questions for the here represented only what is, no, how it's maybe even for second level, for medium level questions, but mostly for the first level question, what is, but not like common for concrete senses that exist in this text. Next. And here you can see as well as system works with graphics, process graphics. For the other type, it's not, if not the graph, but schema, we need as well add information about kind of schema. So as well, we may use now add classification of the task, which type, or whether it's a flow chart, whether it's functional diagram, for instance, in Tau, or anything else. But as well, here example of different types of what is, questions like explain something, or based on this, answer this, or what if, it's higher level questions. Next. And formula processing, as I said, it includes extract formulas, recognize them represented LaTeX, and tutor can edit it with built-in formula because it also may be not correct. In this case, we may use some computer vision tools to rise to improve quality of recognition. But in this upper symbol, lower symbol, maybe small symbol may be not recognized in any case. So tutor may put some edits, and in formula, the first level question is like structure of the formula. And we think about how to do this, and the better way in formula, it's always maybe problem when formula in the text, then understand, no, it's first level, and not understand, but remember the signs for the each variable, yes, for each variable in this formula. And for these cases, we may use replaces and then matches. Replacement with the concrete name of variable and its explanation. Limitations, yes, Boolean algebra and Greek letters is worse. Understanding was for replacement. It's reflected by for replacement that they not correct replaces by xy and x3. Next. Here it is the example. So here you can see formula in LaTeX and how it looks in editor. And here are some velocities or acceleration replaced with x1, x2, here x1 and x2. So we may ask then the questions about which concrete variable must be on these places. Next. No, experiments also was not so maybe complete. It was text pages where was 5 formulas, 7 graphs as flow charts and graphics. maybe not, it's maybe with 7 graphs. And we estimate criteria like correctness, clarity, and relevance. So it was represented to the tutor by these disciplines and estimated by them. Because no, speed as well, we try to estimate speed. It's not so critical in this case. But corrective of information, correctness of information more essential. So easy medium questions gives good result, but hard questions, no, it's natural that 45-70% even 70% may be invalid, not valid from the point of view of tutor, no, of human tutor. No, and formulas, no, they maybe because they less information contain, so they process fastest text, use this concept thesis model as well, so it's slowest. And next, as conclusion, AI tools gives a lot of ability for task creation, reduces tutor workload in this aspect, but tutor cannot remove from this loop in any case. Conceptual thesis model gives some improving for using generative language models for generate different variant of tasks, no, questions. And with more effective, we may create easy and medium levels question. For the future scope, no, it must be integrated. It's completed with their part. It's only for tutors. We need part for students, and then again check our hypothesis that it will be effective for by our students. And introduce interactive tutoring tools. So using these questions not only for test, but as well for tutoring. Thank you for your attention.
So we have questions, so you're welcome.
Thank you for your presentation. You mentioned AI, multiple slides, and I was doing what do AI. Okay, because there are multiple generative models, that's why I was wondering. So that is Gemini. Okay, if you're using Gemini, which be costly for this kind of tasks, if you scale them, like, do you consider this scalable approach to use Gemini to other tasks?
Can we use this model?
Got it. And another question is, do you consider the data sample that you tested your proof of concept on representative enough, size-wise and diversity-wise?
Uncover types of educational material that we have concretely in our department. For instance, it must be some engineering disciplines, connected with programming, with microprocessor, and with mathematical basis of different engineering tools. So we won't cover these different materials and extend the scope of such data.
Thank you. You're welcome.
Thank you for your presentation. The question is, can your approach be applied in solving such problems as software systems development?
Yes, as I'm lecturer, as I'm tutor of programming on the first year, for the first year courses, first year studying students. Programming is area, the main sphere of my interests, but we begin with rather from mathematic base, so mathematical basis of control systems and so on, such a discipline. But programming, no, let's. I say no. We have no such cannot be sure. Not we don't test them on the programming tasks. Generative.
Question. You told that you divide all your data into three parts: text, formulas, and graphs. Did you use this dividing to create tests with different complexity, or what's the reason of this?
No, to use different approach to each of such a representation information. For formula, it will be one algorithm, for text another, and for graphics we need put another additional information to have. But levels, I want that the levels of the question will be the same. First, second, and three, it's better than for generate tests. It's like for generating task. When we generate tasks, the main purpose, I think, it's make more such equations, but which are reasonable enough, not stupid questions. But then it's, I think it's three levels, it's enough to make a trajectory individual and adapted to concrete students and to concrete a task force tutoring mode rather than testing.
One question.
Thank you very much for a nice presentation. I have a question about a conceptual model, which you called the conceptual physics model or something like that. Could you please return back to a relevant slide? Why switching the presentation? Oh, I wonder. Okay. Okay. I didn't quite understand how did you use conceptual model in generating tasks for students?
Conceptual phases model. Conceptual models here, conceptions, all the conceptions that.
Okay. I do accept it.
Conceptual, so not just divide text by some semantic from the point of view of AI, like it looks on the semantic of the text, yes, but it first extracts from the text information in the form thesis, concept, another thesis. So two different theses and deal with one concept. Now
I have an example of that.
Here you can see concept, thesis, not just what existing methods for modeling student ability,
and learning named as this. Another called knowledge tracing ideas, and these two concepts connect with thesis. This method, file efficient, and within conceptual thesis model constructed by authors of this method, construct algorithm which ask first questions of one structure for the first concept, then gives another structure for the another concept, and then another structure for theses. We just put this for, ask for AI, not by the certain algorithm, linguistic, but for this and this.
This is what I do not understand completely. Sorry for interrupting you. For this very example, concept, traditional KT limitation, and so on. This is deep knowledge tracing, DKT, and so on. And the second concept, the superior performance of Saint plus. What has been generated by Gemini in your case, and what has been fed into Gemini through prompting?
By Gemini, it's one prompt. And another prompt, so we not directly ask Gemini, generate our questions of tree level. We first give us sections which consist of concepts, thesis, concept, and then ask the questions to this structure. They are more reasonable than just ask, give the questions.
I didn't look into your paper right now, and I don't remember if you gave examples of your prompts in there. Okay, fine. And if you please allow me just one very short question. The question is about the 10-page training set or whatever. Could you please switch to the slide with 10-page data set?
Like methodical materials for the discipline Tau, the theory of automatic control. And there was some text, formulas, 5 formulas, yes, and 7 graphs.
Just picked 10 random pages from this textbook and assembled the data set, right? Okay, thank you very much.
Thank you for your questions. Thanks for your answers. So, thank you so much. It was our last presentation, and thank you for our presenter. The time is over, so we finish our section. Thank you for attention.